Okay, Cup. Welcome to the fourth class, right? Fifth class, fourth or fifth? Fifth class of emerging technologies for lifelong learning, the spring term. As you will recall, this class is about giving you three things: schema, framework, and library to equip you with the ability to absorb and hopefully partake in the area of emerging technologies, not just what's happening now, but what's going to be happening throughout your career. Okay, so last week we gave you a framework of ingest, probe, survey, and imagine. This is how you sort of like use things like YouTube, whatever, documentary, tutorial, any kind of narrative on a piece of technology, and then you sort of like parse it, work through the structure of the narrative. What's the problem that technology is trying to solve? What solution it's coming up with, and the sort of side effect or further problem or obstacle that has to be overcome, and so forth. Right, and every junction of the narrative has a little point that you can probe further. Reason why this is a problem, reason why this technology is not mature, reason why you need complementary scaling up of something else that the technology relies on. The famous case being the electric vehicle relying on battery technology and so forth. Right, so you can probe those. And each area that you decide to probe, you do a proper literature survey, right? And that proper literature survey is what's similar to what you would do in academic paper. What people have done before, what people have found, and so forth, and basically just go deep into the subject, relying on the previous work that has been done and presented in the literature. And then the imagine part, that's the component or the part of the loop where you actually go into placing yourself in the middle of this emerging technology and try to decide. First of all, you have to decide your role. You can just appreciate it for what it is, or to just be aware of its impact, or literally try to get into the driving seat. Okay, so I'm going to put that under framework. Okay. So it's under framework, right? Before that, we have the emerging technology starting kit, right? That's the idea that several things has to happen for a good idea, or even very clever invention has to become innovation and has to become an emerging area that impacts everybody on a bigger scale, right?
Sorry to interrupt, could you share the screen, please?
Okay, Tap. Sorry. Okay.
Okay,
so that's what we talked about 2 weeks ago or a week ago, right? The emerging technology starting kit, right? What's sort of preliminary or necessary and sufficient conditions and conditionalities that turns good idea, invention to innovation into, say, market success, or gaining traction amongst a wider audience, and turning that into a whole area of emerging technologies that in turn spawn other invention and innovation. Okay, and the IPSC cycle, I've been talking about that, and so we put that in there as framework. Okay, now today I'm going to go a little bit on the library part. Okay, in this case, it's a library for oops, I don't need this. It's a library of a programming language that is useful for visualization and prototyping. Now, I've mentioned before that Mathematica is a professional tool for professional mathematicians and physicists. So it's very powerful in terms of the mathematical functionalities and the analytics capability. Okay, and it also has a very large repository of machine learning models, right? So you can use that as a basis of doing your data science, especially those analytics that are driven by machine learning. But for our class, we are going to use a different feature, which is the fact that Mathematica also hides a lot of tedious boilerplate coding, you know, this kind of like programming technical bits, and sort of like wrap it into a very high level language. And so with that, you can do a lot of prototyping. Okay? And also it has a powerful 3D object modeling or visualization. So for our class, we have I would espouse the use of Mathematica here as visualization and prototyping tool, which is why we have the homework that I asked everybody to go and let's see. Okay, so demonstration place, demonstration Wolfram. Okay, so hopefully all of you have gone and picked your favorite topics to examine, and we might have time. Hopefully, we have time for each of you to sort of like give 5 minutes or so of what you found from fiddling around with this and sort of idea give you. Okay, but first we have to know the very primitives, right? In order to know something about this, we have to, let's say, okay, I'm going to put this on the right hand side just so that it's easier. Okay, fine. So first of all, it's well, what it is, and we talked about that. So let's zoom that a little bit. There's the button. Okay, there it is. Okay. So what it is? So it is a professional mathematician, physicist, computational platform. Now, computational platform implies that you already have the model and you're just trying to compute, but it's actually model discovery, and I won't talk about it at length. But basically, you literally use Mathematica to explore possibility of building the theoretical models of reality. So that's not for us. Okay, that's a library of machine of AI, machine learning algorithm, huge library. Okay, library. Okay, so that's not what we need. We need it for visualization and prototyping with high level language. So we can say and language. Level language for visualization and prototyping. So that's our case. That's what we're here for. Okay. 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 Right. So let's see what's the basic stuff. We need to know in any kind of language. First of all, well, let me multi-paradigm programming language, but mostly used in a functional programming. Okay, but mostly, but mostly use, mostly. I'll put that in double quote. Mostly functional programming. Okay, so with that, you need to know what? Well, you need to know what you need to know about functional programming. First of all, what you need to know, okay? Well, you need to know a few things, right? You need to know the manner and the syntax, right? Manner and syntax, like you come in the morning, you greet "Sawadee krap, Ajahn," you turn on the program. You have to make sure that you know, you do a few things right to start off the calculation. So these are basic things I'm not going to cover, you know, and different languages have its own quirk. Sometimes space matters, sometimes space does not matter. Sometimes you can just do sort of like a very loose, you know, freestyle kind of thing. Sometimes it's very rigid. You have to say A is equal to B, and then you have to have semicolon and whatnot. And if you start with bracket and star, then you can say whatever you like. It doesn't, and then you close it later. So these are, you know, little mannerism and syntax and so forth. But the essence of it is most of the time, okay, the most important thing is the declaration and definition. Okay. Now, declaration has to do with things like what's your variable, okay? Things that can change or something that's a constant. And so you deal with things like, if you say, for example, A is equal to 5, okay? A is equal to 6, okay? And then you write A later, it's equal to 6, right? But if I write it under something like module, okay, don't worry about this. But let's just say, I'll just say B is equal to 6. B plus 1, okay? That's going to give you 7, but when I write what is B later, I don't know, okay? That sort of thing. So these are simple, you know, basically scoping of your definition. Remember that that slide that I used a few classes back. I think class 1 or class 2. I think it was class 2, right? Things you need to know. Okay, it's a little bit like that. On page 1, you can declare anything. Okay, you can assign me to a name. You can define something. Well, it's a bit like that. It's what the variable represents and so forth. Okay, so that's you know, in different languages have different level of specificity. When I was working with C, you have to say that a number has a floating precision or double float precision up to 10 to the 16 digit or whatever. Okay, 10 to the 10 or whatever. I don't remember. So all this is kind of like handled for you in a high level. So this is one of the things. You don't have to say something like, you know, integer B is equal to 5. You don't have to say that because it kind of knows a little bit. Okay. In fact, let's look at this. A is equal to 5. Okay, that gives you 5. And A is equal to 5. Oops, sorry. A is equal to 5 dot. Oops. Okay. It actually knows that if you're putting a dot, you have the intention to, you know, have a precision to it. Okay. So it kind of like does all this sort of thing automatically for you. So that's what I mean by a lot of this thing. For those of you who are not from the programming, don't have to learn. That's a good thing. But again, a quarter or maybe more of you are following me into the rabbit hole of applied digital intelligence, and there you have to learn first of all Python. And you might have to, in some cases, JavaScript, and some of you might even go into C, C++. Then you have to do a lot more housekeeping. So okay. But overall, for this class, oops. Okay, for this class, So all this mannerism and all these things is kind of like handled for you. So that's nice. That's kind of nice. Okay. But you still need to do some kind of declaration. And so first of all, so it's sort of like what the name the variable. Okay. Then you define the scope. Yeah. In other words, you saw just now, if I write globally, A is equal to 5, then it knows it's equal to 5. If I put it inside the module, B is equal to 6, B plus 1 is equal to 7. It does that calculation, but it doesn't know, nobody else does. Nobody else does. Nobody else outside this loop. Okay, for example. So those are basic things. And this is where, I don't know if you have friends in, say, computer program in July, they probably learn things that are like object-oriented programming, and that's very elegant. In fact, I love object-oriented programming, but it does define the scope in a very elegant way. It's like the attribute belongs to you. It's a little bit like that thing that I told you. Okay, the object is a human being. The human being has a name, has a citizen ID, has a genome, has a sex, and that belongs to you. And the way you modify it, well, you can't just modify it willy-nilly. It has to have certain requests, you know. So if the person is going to change his religion, right? You can't just go and change his religion. You have to say, do you want to change your religion? Oh, yes, I do. Then the person changes his religion and so forth, right? So there's a lot of protocol in how you handling this information, okay? So all this data in object-oriented sense belongs to Kumjai, right? And unless Kumjai consents or allows you to modify it, it's my data, that sort of thing, okay? But here, there isn't. Oh, A is equal to 6, I don't care who uses it, everybody knows it. Everybody knows it. So by default, first thing you have to know is by default, everything is global. It's a little bit like internet, okay? Once you type something in there, it's everywhere, okay? So it doesn't matter, you go to 500 more pages, you type in A, it's gonna give you 5, okay? So the way you get rid of that, you have to clear, okay? Clear A. So that's the first function, bracket, fine. So now it doesn't know. Now notice there's a little helper here. If it's blue, it's not known. If it's assigned, it becomes black. Watch this, okay? So let's go back to this. By the way, this is called a kernel. So these are little sentences. These are little sentences. So A is equal to 5 here, okay? A is blue right now because you don't know what A is. So I shift enter again, A becomes black. So A is equal to 5. If I clear A again, shift enter here, it becomes blue again. And now I type in A, shift enter, it doesn't know. Okay, so those are very basic stuff, and we don't need that. In fact, I cover a little bit of that. Most of all this in summer pre-course. So this is a refresher. So this is kind of the sort of thing. Now, the most important thing is the definition part. Okay, why? Because this is how you mostly, yeah, you define object, but you certainly define function. Okay, so you can define function. So let's call it name function. Okay, so definition, there's a built-in. Okay, so definition mostly has to do with function. So built-in function is like 6 plus 5 is equal to 11, right? So you don't have to program that in. Okay, exponential 6798 is equal to this number. Okay, now notice it's not giving you a number. Anybody knows why? Because to scientists or mathematicians, precision is the most important thing, right? When I say 6 plus 5, that's equal to 11, because you can't be more precise than that. Okay, you can't be more precise than that. But exponential 6698, if I give you a number, it's not going to be precise. So it's going to keep it to its It's like when you were in grade school. Teachers always tell you, do all the crossing and the, subtraction, blah, blah, blah. Until you get to the last step, you get one final division. Don't do division before, right? Do carry out all the simplification, then do it on the last step. It's a bit like that. So how do I make it numerical? I just put n around it. Okay. So n of this is equal to there. Now it gives you some kind of number. So that has a machine precision to it. Okay. Now, this is, so you notice now, this is a function. I'm writing, okay, but instead of bracket, round bracket, I use a square bracket. So this is how you define, this is how you use a function. Okay. How do you use it? There's another way. If it's only one variable, you can do this and apply with this. Same thing. Okay. There's another elegant way of doing it. Say this thing, pipe it. Okay. This is what programmer people do. They pipe it, take the result of this, feed it to something else called n. Okay. So whether or not you do this is a function of this. This say you're applying this function to this. This say you take the result of this and then you pipe it. Okay. So this is not so this is very basic. Okay. Built-in function. Okay. Now, of course, what's a plus b? What's 5 plus 6? What's 5 plus 6? 5 plus 6 is actually a function of two variables. It's a function this, add, but it has two variables, 5 and 6. Oops. Sorry, not add, sum. Oh, no. Total. See? Okay, oops, no. What's the function for add? I don't know. Let's add. How come there's no add function? I know. Let's do this. It's a plus, but I just want to know fundamentally it's a function. Okay. So let's go to F1. Plus. Sorry, my bad. Plus. Okay. Right. Now, why do I make a big deal of this? Okay. Because the basic mathematical operation that you learn, okay, it's actually a function. Okay. In this case, and in functional programming, you're almost conscious of what can go in. In particular, how many spots for the input and how many spots for the output. Most of the time, there's only one spot for the output. Okay, but not always the case. Not always the case. Okay, so I can do this. Now, so this is all built in. This is all built in. Okay, now let me define my own function. Add, subtract. Okay, now watch this. This is the most it's the most critical bit you have to learn because you're going to use it all the time. Give me two things. Give me two things. A. Okay. Now, I will put in underscore. Underscore is like a pattern matching. Okay. So this is if you talk to your friend in computing, it's called regular expression, that sort of stuff. But basically, anything that looks a bit like that. Okay. Anything that looks a bit like that, and B. Okay, I'm going to add two things. Now, because this is not built in, right? I can't use it. See, I can't say add, subtract. Nobody knows what it is. Okay, it's still blue. So just as I can say that, A is equal to 5, I can define this as a function. Okay, as a function. Now watch this. I'm going to give you two things. Remember I told you how many spots does it have? 2 spots, A and B. Okay, so the output, well, what if I want to give it 2 spots? Yeah, so I'll give it a list. So A plus B and A minus B. Just, you know, I'm just being whatever. But for some reason, I just wanted to do this. Okay. So right here, right now, okay, I'm gonna add a little bit more feature to it, and I'll go to them. Okay. So think of this. Look at this. Stare at this for a while. It's blue, okay, because you haven't defined it. It's not built in. You give it two spots, A and B. You put underline to match it. So this green thing, this slanted green, okay, when I put it, okay, so A is looking for A. What's A? I don't know what it is. It's blue. But when I say, aha, I put underscore, that means it's looking for things that matches this. Okay, so anything that puts in the first spot is called A in this context. Anything that's put in the second spot will be called B in this context. Then I would do something to A and B. It's equal to, now I put colon equal to. This is a technical thing. It's sort of like what's called delay calculation. Most of the time, you don't want to calculate something and then use it later. Okay, you want to delay the calculation because the component may not be ready. Okay, it's a little bit like you know, you're making fried rice or something. Okay, and soup. Okay, well, you don't want to just fry the meat and then put it in the rice. You sort of like want to put the meat in the rice and then put everything and then blah 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 until it's all ready. You fry it. It's a little bit like that. Okay, so this colon equal is the usual way. Sometimes you just set equality, but most of the time you do this. So I will define this thing. It's blue now. It's going to turn black in a minute. Yeah. This thing is expecting two spots. Expecting two spots. Whatever I put in the first spot, it will be known as A in this context. Okay. So I can put X1 or X2. Okay. But let's say A and B. Okay. Fine. When it takes this, when all the ingredients is ready, it's going to calculate. It's going to calculate, but it's not going to give you one thing. It's going to give you two things. It's going to give you an add and a subtract. Okay. So this bracket here, this curly bracket is a list. Okay. And this just say it's silencing. Okay. In other words, don't have to put the output. But because I'm just making a definition, there's no output. There's no output, right? So now I say add, subtract 5 and 6, shift. It's going to do this, right? So 5 plus 6 is 11. 5 minus 6 is minus 1. So it gives you a list. Now, again, this semicolon that I was showing you earlier, it makes it silent. So if I did this, it did the calculation, but it just stopped output, okay? So sometimes you do that because you don't want to have the output coming out every time. So that's that. That's a definition of a function, right? Now, why would you do this? Why would you define A is equal to 5? You wanted to use it later. Why would you define a function called add, subtract? Because you wanted to do it later, okay? What if you just want to do it once? Sometimes you want to do it once, you don't want to define it, okay? And this is a lot more important than you think because you don't want a lot of definition hanging around, okay? So I want to do it once. I want to do it once, okay? So what I can do is what's called a pure function, okay? A pure function, meaning it's telling you, it's usually something small, okay? Something very small, okay? So this function here can be 1,000 lines long, okay? For example, I can do this. A is equal to A plus B. A is equal to 7, okay? And then I use that thing again. So it's not just silencing, it's actually separating. It's like a full stop in English. Okay, now if I did this, it's a little bit silly. I don't know why I would want to do this. Okay, if I did this, the sad fact is it's no longer allowing you to be any A. It's going to make A into 7. So if I did this, okay, it's going to say, cannot set a raw subject to 5. Oh, okay. Yeah, no, it can't do that. Sorry. Let's say something like C is equal to A. Okay. And again, C is something else. And then C, okay, I can do that. Okay. Okay. And now it's going to do the same thing, but it actually separates into 2 steps. Okay. Now, when I did this, that's not good because C is actually now a global object. So what I want to do is I might do what I did earlier, which is something like mod2 C. Yeah. Okay, you don't have to pay attention to this. I just want to show you that this is the structure of what it looks like. Okay. Okay. Yeah, something like that. Okay. Now it does this. So the thing I want you to notice is that it can be many steps. Okay, this could be 1,000 steps. I'm just writing 2 for some reason. Okay, and it has a local variable. Okay. Now, so you would do this. You would name this function if it's something that you use a lot and it takes 1,000 steps, right? You don't want to write a new step every time. So this is a built-in recipe. That's what a name function is. But sometimes you just want to use it once. Okay. Sometimes you want to use it once, you can do this. You can say, I want to take some variable. Okay, take some variable. Okay. In this case, it's a little bit like that underscore. It says something like plus 5 and the whole thing divided by, okay. By the way, you use control and underscore. You have this in yours, so you can play along. Okay. So let's say I do this. Okay. So I'm actually not naming this function. Okay. I'm not naming this function because it's so simple. I'm going to use it once. Okay. But I want to do it. So I take something, add 5 divided by 7. Now there's a sign called ampersand that turns this into a variable. This is called, well, this is kind of like inline function. When you do this and now it becomes a function. Now it becomes a function. Okay. And then apply to something, some number, 9. Okay. So it's going to give you 45 divided by 7. Huh? Sorry, 14 divided by 7. Okay. This is a lot more useful than you think. Okay. Because in a lot of function, you want to perform something very specific. Okay. Just right there. You may loop this 1,000 times, but just right there. Okay. So this is, so in other words, this would be something called a name function. This would be called an inline function. Now, let's do this. Let's make this an inline function. Okay, let's go back to forget this mod2 here. Okay, it's there. Okay, so again, I'm just making this thing. Okay, this is your calculation. Okay, so you know that add, subtract 5 and 6 is equal to 11 and minus 1. Okay, so you name this. Now, again, if I wanted to do it once and only, okay, I just say, I want something. Oops, sorry, something. Now, there are 2 something. So let's make it 2 something. Something number 1. Okay. And something number 2. Now, I don't want to define a name. I just want to do this. So that's what exactly I'm going to do. Except I call this the first thing, the second thing, the first thing, and the second thing. And this is the notation. Okay. When you learn Python, again, a quarter or more of you are going to apply digital intelligence. This would be equivalent to what's called lambda function. Okay? So it's a little bit like inline function. So now I can apply two things, 5 and 6. I get this. See, same thing, right? Okay. So this thing is a name function. This thing is an inline function. Okay. And just to confuse you, and you can completely ignore me after this, okay? You can do this as well. Add, subtract, version 2 is equal to this. So you do an inline and then you name it. Okay, so this is a name function. This is an inline function. This is naming an inline function. Okay, most people don't do this. Okay, it doesn't look nice, but you can do that, right? And then you can say add, subtract version 2 later. Okay, and then 5 and 6. And then you get the same thing. Okay, sometimes you do this perhaps because you wrote something you wanted to use once, but you realize, wait a minute, I want to use it again or something. Okay, but this is, you don't see this that often. Okay, you see this a lot, mostly followed by many lines of things. Okay, so that's why this is important, because when you have many lines of things, it can do many calculations. And when you do many things in calculation with various conditions in between, like if x is greater than 5, do this. If x is less than 2, do that, blah, blah, blah. Do this until you run out of things to do, blah, blah, blah. It becomes an algorithm. Okay, so let's go back to our little diagram. So you have built-in function, you have name function, and then you have inline function. But because these two are actually user-defined or programmer-defined function, okay, I'm going to put this to here. Okay, so definition, built-in function is already defined for you. Okay, user-defined function, you have to define it. Inline function, it's maybe something very tiny, very precise, use one. And name function, this is especially useful for encapsulating or coding an algorithm. Okay, it's useful, and this is where you come in. So just as in this lecture, in that previous lecture that I told you that, you know, what do you need to know? All the statistics, all the distribution, at the end of the day, it becomes a function. Everything here, in fact, you know, if I have a lot of time, I can literally go through every pages of what you need to know here and translate to a mathematical equivalent. Okay, statistics, distribution, function, calculation, lookup, whatever. Okay, I may do that for some example. Okay, so all these operations, okay, distinguish this statistical discipline, all this has counterpart in real functional programming word or program functional programming function. Okay, so this is where you do everything. Okay, now let me just take half a minute to distinguish between this and object-oriented programming. Object-oriented programming, again, everything is like a human being. As personal data has a way of modifying it. You don't get to modify it directly unless you ask the person to. Okay, so in that environment, all the interaction is between little human beings in the program. Okay, little collection of data, and that's called an object. Okay, now an object belongs to a class, so that a human genome and frog genomes have different size. Let's assume human genomes bigger than frog genomes. Not always the case. Sometimes simple animals have huge genomes. So all human genomes are this long, all frog genomes are this long. Okay, so that's why human can reproduce with human, because you can cross same size genome. You can make a human frog hybrid because there's not enough space in the frog genome to accommodate human genome, and there's not enough frog genome to fill up all the spaces needed to make a human. Okay, so that's the concept of object oriented. It's about data and what you can do with it, operation you can do with it, and it's all separated into little nuggets of entities called object. Okay. With functional programming, you also have this kind of encapsulation, but you're not so focused on the data part. You focus on the functionality. You wrap everything inside a function. Okay, just like in object-oriented programming, you kind of wrap things into object, which contains data and operation. Now, the operations themselves perform function, but you don't see it that way. You see it as operation on the object's data. Okay? That's their paradigm. That's object-oriented paradigm. In functional programming paradigm, again, this is very much in line with the what you need to know slide that I gave 2-3 classes ago. Everything is wrapped as a function. Okay, so if you want an omelet, you have a function that makes an omelet. That function in turn calls a function that cracks an egg, calls a function that turns on the heat, calls a function that put the egg that has already been cracked by that function called cracking the egg into putting in the pan function. So everything is function, getting the input, do something, output, send it to another function. Your job as a programmer, so what's your job as a programmer? Your job as a programmer is to define functions and how they are linked. Yeah, so there are two things. So your job, so that's what you need to know. Your job as a programmer is to, one, define the functions you may use. Find the function. Okay, so instead of saying define all the functions, just say make sure you have all the functions, because some of it's already built in. Okay, make sure you have all the functions you need. Okay, all the, make sure you have all the functions. Required function. Yeah, make sure you have all required function. Then orchestrate or arrange, know how to arrange them to perform tasks. Okay, arrange them or orchestrate or arrange them to perform tasks. That's it. That's two jobs. Okay, now you will notice that the way things happen is like this. You want to do something. Again, you want to make a fried rice. Okay, you want to make a fried rice. If you're going to make it once, you never make fried rice again. You just crack an egg and do it. Okay, that would be something like inline function. You do it once. But if cracking an egg is important to you because you're making fried rice with eggs, but you're also making souffle requires egg. You're making cake requires egg. It would be nice, and let's say cracking an egg is a big job. Okay, what you would do is define that function like a name function called crack an egg. And this, the first time you would use it, you crack an egg, take the egg, put it in the pan. But then you keep it. You keep it in a library of function. And later on, you use that library to access that library and say, I'm going to crack an egg, but I'm not going to use it to fry rice. I'm going to use it to make souffle. I'm going to use it to make cake. So that's why this thing, okay, once you've done enough, it becomes like a library. Hence, library. Okay? Now, because you're a nice person, you know how to crack an egg in a very nice way. Other people crack an egg and get bits of the eggshell into it, but you have a nice way of cracking an egg to get all the egg white, egg yolk, very, very, very nicely ready to prepare. You share it. Okay, and this is how the world advances. You build the library and you share them, and this is where you have open source. Hopefully, if it's, by the way, to make an open source, first of all, it has to be a good thing, right? You don't want to share a lousy way of cracking an egg. So you share. So this is what's called open source, especially open source. And this is how the world advances. Yeah. This, by the way, this is how Python takes over the world, because the open source community is large. Okay, so it's a number game. Mathematica libraries are developed by people who work in Mathematica and people who work independently like me, but usually we don't have much to add. Okay, because Mathematica is already very powerful, so I don't really add much to it. I basically do this. So there's a function that calls function. So these are application functions. Okay, so I would say this hence library of generic function. Yeah, and this is IE task specific function library. Yeah, task specific function. And this, I can share. It's sort of like a if you just want to do everything from the beginning to end, from egg to souffle, I can do that. Okay, so sometimes this is also share. Okay, so this is also share. So both of this, maybe I should do this. Sorry. Especially open source. Okay, that's what you do. But you share both, but certainly the primitive, the generic function is. So things like machine learning algorithm, By the way, I'm going to show you something like, this is a very good website called Paper with Code. Paper with Code. Okay. This has all kinds of stuff. Okay. Neural differential equation. Let's say I go in here. It has a link to the paper. It also has a link to share open source library. When you go in here, you will find that a lot of it is kind of generic, but a lot of it is specialized. Okay, so you can think of this as generic function, and this is more like a task specific. Okay, task specific. and you can use both, because even if you see task specific that is too specific, in other words, it doesn't apply to your data set, you can modify it. Okay, you can modify it. But of course, when you use it, be sure to thank think kind thoughts or attributes in your paper, right? So you're using that code, you think kind thoughts of them as you're using them, and when you write your paper, you reference it. Okay, fine. So that's it. So that's what you need. That's all you need to know about what I call functional programming, in the sense that you need to know. Okay. Now, as a prototyping tool, okay. Yeah. So as a prototyping tool, let's see where we are. Oops. So let's go to almost like a use case kind of thing. Okay. Use cases. Okay. So let's say demonstration. Let's put that website here. Wolfram demonstration project. Wolfram demonstration project. Okay. Now here, there should be 10 of them, right? Each one of you. Okay. Who wants to volunteer to go first, maybe? Oh, okay, I can hide this here. Okay. Keeps getting in the way, and I can't see the bottom. Okay, now I can see. Larger demonstration project. Okay, use cases, demonstration project, and maybe I have something of my own. For example, I think I might go over COVID. COVID-10 data analytics. Right. So who wants to go first, or who wants to give a who thinks that they found a good one? Anybody? Okay. Well, if not, then let's take one video break, and then we'll come back. Back up.